Hello viewers, welcome to this next lecture of our series of lectures on elementary quantum mechanics. In today's session, we will continue with our understanding or the discussion on hydrogen atom. And the session here today is planned as follows. Initially, I will try to give you a brief review of what we did in the previous session, and thereafter I will take up the main crux of today's session, that is we will take up that when you solve different wave equations which we get from the previous session what we got here, that is the phi equation, theta equation and r equation, we will talk about what kind of results do we get and what is the significance of those results. So, that is what the main plank of today's session. And thereafter, having done that, we will learn about what is the significance of quantum numbers which we get in the process of solving the Schrodinger wave equation, the three components of that. So, that is what I am going to talk about in today's session. Let us make a beginning by recalling what we did in the previous session. You would recall that to begin with, in the previous session we defined the problem of hydrogen atom. We realized that it is a two particle problem. There is a nucleus, there is an electron, and this problem was difficult to solve because when it is a two particle problem, we have as many as about 6 parameters or 6 variables in the equation, which gets very difficult. So, thereafter, since it was a difficult equation to solve, we explained the reasons for. The first thing we did was how do we separate the Schrodinger wave equation into two equations, one for the center of mass and second for the relative coordinates. Center of mass referred to, that means a molecule is moving, the atom is moving as a whole, as one particle, and relative coordinates meant was that we had a nucleus, we are talking about the motion of electron with respect to the nucleus. So, there are two things we separated in the first instance. And then thereafter, we took up the equation which pertained to what is called as the relative motion, because that is of interest to us, because we wanted to know how does the electron behave in the atom. So, to do that, we realized that this equation was again not solvable, because one small parameter there, that is radius, that is the distance r, because r was creating a problem in separating this equation into smaller variables. So, to sort out that issue, we transform the equation into polar coordinates or the spherical coordinates r, theta and phi. So, with that kind of a development, we realized that we could solve this equation, we can separate these equations into three smaller components, respectively the r equation, theta equation and phi equation. Mind you, we did not do, because it is not in our purview of this course, to how do we do that. What we did here was that why do we need it and how do we do that. So, we did not actually do that, but we we discussed about the pros and cons of what we are doing and how do we do that. And as a result of all that, we were able to get the three equations, the phi equation, theta equation and the r equation, and these equations are then solved gradually. Today, what we will do is, now we will see if I solve these equations, what kind of results I am getting and what is the significance of those results. That is the main plank of today's session. Okay, let us make a beginning. And what we do is, when we try to solve these equations from mathematical convenience point of view, because these three equations are interrelated, though they are separate equations, one depends on r only, one depends on theta, one depends on phi. But from mathematical convenience point of view, what we do is, we solve the phi equation first, the simplest one. Thereafter, we go on to the theta equation and then to the r equation towards the end of it. And when we solve these equations, we ensure that this equation, when you solve, they adhere to the boundary conditions. You will recall from our earlier sessions that any solution of a wave equation must meet the boundary conditions. So, we remember, say, particle in one dimension box or particle in 3-dimensional box, we ensured that the wave equation what you are getting, the functions we are getting there do accommodate or do confer to our boundary conditions. So, here again what we do is, we ensure for our r equation, that is the wave functions what we get there must approach to 0 as r tends to infinity. Similarly, for theta and phi, we had to ensure that the values of these wave functions are finite for the relevant angle ranges. Say, for theta, we know that the angle ranges are 0 to pi, and for phi, we have got 0 to 2 pi. So, for these ranges, we must ensure that we do ensure in the process of solving these equations that the boundary conditions are met. And similarly, for the phi equation also, we have to ensure that this equation is periodic in nature. What it means is that if I take phi, r theta phi, that is this wave function and the one r theta phi plus 2 pi must be identical. That's the meaning of periodicity. That means the wave function repeats after every 2 pi. So that means a function at 0 pi, 0 phi and 2 pi phi must be same. So that is the meaning of periodicity. So okay, so these are the things what we ensure in the process of solving it. Now we come to what are the results we get there. Look, let's start with looking at if I take phi equation or the phi equation and solve it, what do I get? Before I proceed, I would like to recall for you that when you solve an equation, let's take a simple example of a quadratic equation. Say ax square plus bx plus c, let a, b and c have some values. Okay? When you solve this equation, what we get is we get two solutions. Say x1 is something, y1 is, y2 is, x2 is something else. That means you get two solutions, x1 and x2. And what do the solutions mean? That is, this equation which I have taken as a quadratic equation must be valid for these two solutions. That means if I substitute these solutions into my equation, the equation should be valid there. So that's the meaning of a solution. Similarly, when I solve the differential equations, what I get here, the r equation, theta equation, phi equation, when I solve them, I get something called as a solution to that as the wave functions. So when I am solving phi equation, I get a series of wave functions which I called as phi m, and they all wave functions phi depend on the variable phi, and they have an expression of this kind, 1 by 2 pi square root e raised to I m phi. We are not bothered about what's the expression here. What we are interested in is what is the meaning of this. The meaning of this is that I am getting a series of functions. That means I am getting a series of solutions there. That means there are infinite number of solutions for which this equation is valid. How do we say that there are infinite number of solutions? Because what we get is that we have a parameter called as m, which is a quantum number. And this m has a value of 0, plus minus 1, plus minus 2, plus minus 3, up to plus minus infinity. So if I put any value of this, say if I put m is equal to 0, I get one function. If I put m is equal to plus 1 or minus 1, I get another one. So I get a series of functions when I substitute this value of m into the generalized equation which I got in the process of solving the phi equation. So I am getting an infinite number of solutions. And most importantly, the outcome of this is the two things: one, a series of wave functions, and two, a quantum number called as the magnetic quantum number, whose values are 0, plus minus 1, and so on and so forth up to plus minus infinity. You will be maybe kind of trying to relate with what we know from your earlier knowledge, that m doesn't have these values. We'll come to that as well as we proceed further, because they are not the ones which we are familiar with. How are they different and why are they different? We'll come to that. Now, so when I solve phi equation, I get series of functions and a quantum number m. Okay, so these are just a small table which shows you that if I put, say, m is equal to 0, I get this as a function, m is equal to plus 1. So just basically in this expression here, I am putting different values of m, I am getting series of functions over there. So each one of them is a solution to the phi equation which I got in the as a process of separation of variables for the wave equation for hydrogen atom. Okay, when I proceed further to my theta equation. What do I get now? What do I get now is I get three things now. First, I will get a series of functions. So now theta, Lm, theta. This theta is my variable, and this theta are the wave functions. Forget about this expression. And what you have is, we have another expression here which basically are associated legendary polynomials. What are these? It's not an overview. What basically I am trying to show here is that the wave functions what we get are little complicated ones, and because these things come in the process of solving the equations. Because I took the example of quadratic equation, we know how to solve that. It's a very simple method. Similarly, to solve differential equations, one of the methods is what is called as a series solution method. So in that case, we use polynomials and things like that to work out the solutions. So this phi equation or theta equation is solved in the same fashion, and accordingly what you get is a series of wave functions which look very complicated, but they mean what is very, very simple to us. We'll come to this little later, maybe in the next session we talk about it. Then another thing what we get is, in addition to the wave functions, I get a new quantum number called L, which is called as the azimuthal quantum number. we'll talk about significance as we proceed further. And what we find is this azimuthal quantum number has a value of 0, 1, 2, 0 and all positive integers up to infinity. So that is the second thing we get there. When we solve phi equation, we got two things, wave functions and a quantum number. When I solve theta equation, I am getting three things now. One, a series of wave functions. Two, I am getting a new quantum number called as L. Thirdly, very significantly, what I get is a restriction on the value of m. What it says is that when I solve this theta equation, I find that this equation must hold true. That is, modulus of m must be less than or equal to L. That is, I am putting a restriction on the value of m now. Now, if I try to see, we had the value of L to be equal to 0, 1, 2, 3 up to infinity, and since mod of m can have a value of less than or equal to L, so my mod m now becomes 0 up to L and not up to infinity, because depending on what value of L I have values of m also dependent on that. Or in other words, we can say our value of magnetic quantum number m now has the values, possible values are 0, plus minus 1, plus minus 2 up to plus minus L, and not till infinity. L may not be infinity at all. We will come to that as we proceed little further. Okay, so we got phi equation solved, theta equations result we have seen. Now typically if you look at the theta equation and the phi equation, both of them involve some kind of angular component, and normally what we do is we club these two equations, because the theta equation and phi equations, the wave functions, they are clubbed together and what you call it as the angular part of the total wave function, because our wave function is psi is r theta phi. We have got r in function of r, theta function of theta, and phi function of phi. So the product of 3 is the total wave function we have. So after that whole wave function, the angular component, that is what depends on theta and what depends on phi, they put together is called as the angular component of the wave function, and that is given expression like it is y, and that is the product of the theta wave functions and the phi wave functions. Now we proceed to the R equation. Okay, when we solve R equation, we get even more information. One, we get series of wave functions again, and forget about this expression is there just for sake of it. But what it conveys is that we are getting a series of wave functions which are solutions to the R equation, and all these functions are having dependence on a new parameter called as n, the principal quantum number. So that's a new quantum number we got there, and these radial functions they are called as, they will be dependent on the value of n and L both. We'll come to that. So we got a series of wave functions. 2, we are getting a new quantum number called as n, which has a value of positive integral values 1, 2, 3 up to infinity. So got two things there. Thirdly, what we get is we get a restriction on L. When we solve phi equation, we got m. Solve theta equation, we got L and a restriction on m. Now when I am solving R equation, I am getting a new quantum number n and also putting a restriction on the value of L. When we do that, what we find is that the restriction of L is it has to have a value of less than or equal to n minus 1. What it implies is, since L has got these values, so we say that L can have a value of 0, 1, 2 up to n minus 1, where n has a value of 1 up to positive integer values 1, 2, 3 up to infinity. So what do we get? We get 3 sets of quantum numbers. So in addition to the wave functions and the quantum number and a restriction on the value of L, we get another expression called as the energy expression, which reads as that En to be equal to 2 pi square mu z square E4 by n square h square, wherein 2 pi mu z E and h, they all are constants. That means all these terms become constant. So what we say is that energy is inversely proportional to the square of the quantum number, the principal quantum number. Okay, that is, my energy is inversely proportional to the square of principal quantum number. That's one significant observation we have. Secondly, we have is that this energy has an expression, there is a negative term over there, that is, energy is negative. Now what it means is the following, that suppose we have got a nucleus here, and let me imagine that my electron is at infinity. When the electron is at infinity, so there is no attraction between the nucleus and the electron, and that is taken as the zero energy. So as the electron comes closer and closer to the nucleus, the energy is decreasing. That is why this energy expression gives me a negative term there. Okay. So, more about it as we proceed further. So, the two things, energy is negative and energy depends only on N, not on L and M. And thirdly, this expression is exactly the same what we got in the case of Bohrs model. So, it is very interesting to note that what Bohr gave was a very semi-quantum model, and what you are getting here is from wave mechanics we are getting an expression which is identical to that, which amounts to saying that the results of hydrogen atom spectrum which are explained fairly well by Bohrs model, they are explained equally well by our Schrodinger wave equation. So, that is a very significant thing. So, having learnt about the energy expression, let us try to analyze the energy expression we have got. And before I get into that, let me recall for you, that is when we defined our system, we defined the system to be hydrogen-like ions, not only hydrogen atom. Hydrogen atom was one such system. That means my equation which I kind of formulated initially and solved thereafter was for hydrogen-like ions, which meant hydrogen atom or helium ion, helium plus, or lithium 2 plus or beryllium 3 plus. So, all of them are two particle problems. There is one nucleus and one electron. So, this is one electron problem there. Now, when I do that, that very fact is being reflected in our energy expression here. So, what we see is this term Z, Z is your nuclear charge. If it is hydrogen atom, it is 1. For helium ion, it is 2. For lithium, it is 3, and so on and so forth. So, what I do is I just rewrite this expression by substituting the value of all the constants here and segregating Z and N term here. So, I get a value, an expression to be equal to minus 13.6058 electron volt into Z square by N square. Now, that is a general expression for all the systems I have just talked about. If I take Z to be equal to 1 and N also to be equal to 1, that means I am talking about hydrogen atom, and when I take N is equal to 1, I am talking about the ground state of hydrogen atom. When I do that, so I find that En comes out to be minus 13.6058 electron volt, because this term becomes 1 now. What is the significance of this term? That is, this term tells me that if in case of hydrogen atom an electron comes from infinity to my the 1s orbital or the first level over there, or the ground state of hydrogen atom, that gives me a stability of about 13.6 electron volt. Now, if I give energy to this atom, energy equal to about 13.6 electron volt, what I am doing is essentially I am taking this electron away from the hydrogen atom and throwing it away to infinity. That means I am going to ionize. So, this is a measure of the ionization energy of hydrogen atom, because I am sure that you all remember from your school days that the ionization energy of hydrogen atom is 13.6 electron volt. So, that comes from right here. Same on the same terms, you can work out, suppose I put Z is equal to 2, I can work out the ionization energy for helium atom and other atoms as well. So, this is a generalized expression which can be used to work out the ionization energies or the energies of different orbitals for different kind of systems or different kind of hydrogen-like systems. So, this picture tells us, this is similar to what we saw when we talked about Bohrs model's validation. We find the same thing over here. That is, this tells about basically about the different energy levels. So, when N is equal to 1, energy is 13.6 electron volt. When N is equal to 2, energy will be proportionately less. 3, 4, 5 up to infinity, infinity will be 0. So, when the electrons come from higher level to lower level, when they drop down, they give out the energy in form of the radiations, which we observe as the line spectra, the Lyman series, Balmer series and things like that, which we talked about earlier also in case of Bohrs model. So, what you find is there is a one-to-one equivalence between what we had in case of Bohrs model and Schrodinger's mechanics, because what we are getting is an expression which is identical to that. Okay. So, what we got in this, when you solve these equations, we get two things. One, the total wave function for hydrogen atom, and the total wave function you would recall is dependent on all the three parameters r, theta and phi, and actually in fact it is a product of the three parts, that is r part, theta, or you can say the angular part and the radial part. So, that is the wave function we got there. And secondly, what we got is we have got a series of quantum numbers N, L, M and MS, we will talk about that as well. So, we got two things. series of wave functions or the total wave function and also the quantum numbers. So we need to understand the significance of these. As regards the wave functions, we will take up in the next session. For right now, we will take up the significance of the quantum numbers which we have got. Let's understand that. And before we continue there, let's see, just put them together, that we can recall that n has a value of 1, 2, 3, 4 up to infinity. L has a value of 0, 1, 2, 3 up to n minus 1, where ml, the magnetic quantum number, has a value of 0, plus minus 1, plus minus 2 up to plus minus L. And in addition to these three, we got one more quantum number which doesn't follow from our Schrodinger wave equation, but has been imposed from outside. That is called as a spin quantum number. That is given a value of ms to be equal to plus minus half. That comes from outside. We will talk about that as we move further. So we take up the significance of these quantum numbers. We start with the principal quantum number n. Principal quantum number n quantizes energy. This is what we got when we talked about the energy expression, because we remember that energy was proportional inversely to the principal quantum number n. And secondly, this also is related to the distance of electron from the nucleus, because as n increases, we go farther and farther from the nucleus. So n tells two things: it quantizes energy, and also it tells how far is the electron from the nucleus. Larger the value of n, farther the electron from the nucleus. So those are two big things. In addition to that, this principal quantum number n defines a series of shells of the atom. That means when I say n is equal to 1, there is only one shell. When n is equal to 2, L can take value of 0, 1, and m can take values of depending on the values of n, L. So all these put together define what is called as one shell. So what we are having is, in case of an atom, we have a nucleus, there are different shells, and these shells are defined by the principal quantum number. So n refers to, n is equal to 3, means I am talking about a third shell outside the nucleus. Okay. And all the subshells, which will come to when we talk about the quantum number L, the subshells will have the same energy, and they are called as degenerate over there. The second quantum number is azimuthal quantum number L. That actually is the one which quantizes the angular momentum of the electron. N was quantizing the energy, L quantizes the angular momentum. And in fact, if you really look at in colloquial terms or in common terms, L is related to the geometrical shape of the orbital what we get there. If L is equal to 0, we have spherical shape, s orbital. L is equal to 1, we got p orbitals of a dumbbell shape kind of, and so on and so forth. In addition to that, what we see is that L is has a value, that L is the angular momentum, has a value of L into L plus 1 square root h cross. That means the angular momentum is in terms of h cross, which is the unit of which is called as action constant or unit of angular momentum there. So it is quantized here. Now what does this mean? This is very significant thing again. Let's try to see. If you recall that when we talked about Bohrs model, you would recall that in case of Bohrs model, we had only one quantum number n, and that quantum number was quantizing the energy as well as angular momentum, because you remember that E was equal to h nu, that is the quantization of energy, and our L was equal to nh by 2 pi. That means it again was quantized. That means the L, the angular momentum, was also quantized in terms of the quantum number n. Whereas in case of Schrodinger mechanics, what we got is, we got two different quantum numbers, n which is quantizing energy and L which quantizes the angular momentum. That very significant differentiation from what we had in case of semi-quantum model and a quantum mechanical model. Yet another thing what we can infer from here is, that is L can have a value of 0. When L can have a value of 0 means, because we didn't have that possibility in case of Bohrs model. In case of Schrodinger mechanics, we can have L to be equal to 0, which means the electron doesn't have angular momentum, or in other words, it means it belongs to s orbital, a spherical shaped orbital. We'll talk about that in the next session. The third quantum number is my magnetic quantum number, or ml. M depends on the value of L, so it's given as subscript of L there. And this quantizes the z component of orbital angular momentum. Let's take an example, understand. And actually the expression here is that Lz is equal to ml into h cross. H cross is the unit of angular momentum and ml are the different z components of the angular momentum. Now, and if I take say L is equal to 2, that means my angular quantum number is 2, then the angular momentum will be equal to 6 h cross. That means this is a vector which is of unit of h cross. There 6 h cross is the magnitude of that vector of angular momentum. What it means is, if I take the projection of this vector, which is of dimension of 6 h naught, this can be this orientation, or this, or this, or this. It can take up only certain orientations, such that if I take a projection of this from here to here, this will be 2 h cross. If I take this one, this will be 1 h cross. This will give me projection of 0, -1, -2. That means the angular momentum vector can take up only those orientations which give a projection of a quantized value. That means m can have a value of 2, 1, 0, -1, -2 for L is equal to 2. So, there are 5 different values of m for a given value of L. So, the two are interrelated. That is why we put it as m subscript L, because value of magnetic quantum number depends on the orbital that will be angular momentum quantum number or the azimuthal quantum number. And also, if you see in a common term or a colloquial term, this m tells you about the orientation of the orbital. We will talk more about it in the next session when we actually look into these wave functions, interpretation of the meaning, and how do what are the shapes of different orbitals. That is a very interesting topic which we will be taking up later on. Okay, let us move on to the next quantum number called as the spin quantum number. If you recall, I just mentioned earlier that this spin quantum number does not follow from our Schrodinger mechanics, because when you solve these equations, we have got only 3 quantum numbers, n, l, and ml. This quantum number, the spin quantum number, was introduced later on to account for an experimental observation, because people, when the Zeeman effect and Stark effect, you must have learned about that in your school. That is, when we look at a spectrum of say hydrogen atom spectrum in presence of magnetic field or electrical field, we find that there are more lines than what are predicted by the Schrodinger mechanics. And to account for that, it was proposed that these lines can be accommodated or accounted for by ascribing some kind of an intrinsic spin to an electron. That is why there are only 2 possibilities, that is, the spin quantum number can have a value of +12 and -12. And in common terms, we try to visualize this as an electron moving clockwise or anti-clockwise, though the electron does not move per se, but that is the way we try to visualize it. So, there are 2 possibilities by which we can recognize with these 2 quantum numbers. Okay. So, let us sum up what we have done today. What we have done today is, we briefly reviewed what we did in the previous session, that is regarding the formulation of Schrodinger wave equation for hydrogen atom or hydrogen-like ions, and then thereafter how to and why to make it simpler so that we can solve that. And in the process, we got 3 equations, R equation, theta equation, and phi equation. And in today's session, we have tried to see that when you solve these equations, what are the outcomes of that? The outcomes are in terms of the wave functions and the quantum numbers. And we have seen that what kind of wave functions are we getting there, and what are the quantum numbers, and what are the interrelationship between the quantum numbers. And then thereafter, essentially we got 2 chunks of information, set of wave functions and set of quantum numbers. And we have seen late towards the end the significance of the quantum numbers what we get. In the next session, we will take up, we will look into the meaning of, or we will try to see what are the shapes of different atomic orbitals. Because if you look at the wave functions, if I plot them, what kind of information do I get? What do they mean to us? So, that is all we are going to take up in the next session. That is, we will focus primarily on to the interpretation of the wave functions what we got today. Thank you.